It's light. Hi, everybody. Thank you for coming to see my talk about Java in, yep, that's the right one, good. Java in the world of containers at Container Days on a boat. This is quite unusual for me. I don't know if all the Hamburg conferences are on boats, but it's nice. So, this talk's 35 minutes. It's quite short for the content, so if I go too quickly, shout at me. I'll slow down, but I'll try and get through everything. Probably no time for questions at the end, but please find me, Bright Blue, or my Twitter handle is on all the slides except this one. So let's go. There it is. So my name's Matthew. I work for Oracle, and I work on an open source project called FN Project. FN is a serverless compute platform where all the functions are defined in terms of container images. So what FN does, you upload an image and you say this is a function. You upload a container image to some registry or other, and then on demand we execute that container. I'm not going to talk very much about serverless or FN. My job on the FN team primarily is the Java support. And of course, FN, the kind of project it is, we stop and start containers containing Java all the time. And I've learned a few things. Working for Oracle, I was able to work closely with the Java platform group. So I would like to share with you some of the things I've learned. And I was a Java and Clojure programmer for many, many, many years before I started working on cloud infrastructure. So I kind of feel the pain of it. So basically, Java seems like quite a good fit for containers. Initially, there's, I need to read up here, the managed runtime, right? You as a Java programmer, you don't really do much systems level programming. It's all application level. You don't deal with memory or threads directly. You deal with the abstraction. In theory, your code is not even caring about where it's running. And runtime adaptive is the phrase the Java platform group used to say your code should run the same anywhere, right? So this seems like, because of these characteristics of Java and the JVM, that it should be a pretty good fit for containerized deployments, which are becoming more and more popular. But it's not perfect, and there's more that you can do, and there's more that you can get the JVM to do for you when you're running Java in containers, right? So if I ask you for a show of hands now, who's a Java or some JVM language engineer, programmer, developer, whatever? Right, most. And using JVM in containers? That's more than before, okay. and in production? Awesome, well done. Using Java 10? One person, good. Okay, Java 6, 7, very brave for the 6 there. 8, right, that's as I expected. 9, like why would you use 9 when 10's out now? 9's not supported anymore. Okay, right, so crack on. The 3 things I want Java to do in a container are these 3. Start quickly, okay, especially non-Java JVM languages have this extra problem of a language runtime bootstrap on top, but even just the JVM itself has some reputation for slow startup. Especially in the serverless world, that's a big deal, right? Small container images and respecting the environment. So when I say respecting the environment, what's a container? To me, it's like a sandbox of a process that runs on a host, and the rules in the sandbox are a little bit different. And if you don't follow those rules, and the application you're running, which is the JVM, doesn't follow those rules, then you're going to have a bad time. So I'll go through these 3 things the rest of the talk, and I'll give you specific information about what you can do and what the JVM can do for you. I will demo some things. Perhaps they'll work. We'll see. Right, crack on there. And so fast startup. This is obviously super important for serverless. Every serverless platform is measured in terms of its cold start. People as well talk about Java as being unsuitable for command line applications and things because there's just a not responsive feel. You type something and it takes half a second of just extra time before your application runs. That's not good. So some of this applies to just regular Java usage outside of containers as well, but it's also super important because the idea of having more JVMs rather than a big shared JVM, a big shared web logic or something, more JVMs that are started on demand is prevalent, right, with containers. So what can we do? Well, I'll tell 3 things, right? And those 3 things are basically 3 versions of the same thing. The tip is, like, move startup activities to image creation time, right, to build time. So when you type Java -jar, blah, 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 you press return, the JVM process starts up, and a lot of things happen, right? It's a complicated piece of software. And many of the things that happen are entirely deterministic, right? So you get the same result every time. They take time. It's the same calculations and the same result every time. So the trick, or the tricks that I'll show here, are about doing those things in advance and caching the result in a more quick-to-load format, and then using that cache next time you start up. And I'll demo those, a couple of those as well. So thing number 1 out of those is class data sharing. So who's using class data sharing? 1 person. 0 people, he's not sure. Class data sharing has been available since Java 5, so it's almost old enough to drink, I guess. It's 2004 that Java 5 was released. I don't know the drinking age in Germany. Maybe it is old enough to drink. And so when you start JVM, a lot of core Java classes are loaded. They're stored with the JVM on disk in bytecode, right? Java-lang object, Java-lang string, util hash map, like all that kind of stuff that every application uses is stored as bytecode on disk, right? And the bytecode is loaded, parsed, verified, some kind of relinking step that I'm not enough of a JVM internals expert to know the details, but there's a relinking step. And all this takes time, and what you end up with is an in-memory data structure representing the loaded classes. And what CDS does, it just serializes that to disk, and then when you use that cache that's been serialized to disk, that file is memory mapped in with like much, much less overhead. So if the Get Demo gods are with us, can you read that? If you can't read that at the back, there are some seats at the front. No, is it big enough? Yeah? Good. No one said no. All right, and this is my only way of seeing the screen, so it's a little bit funny. Where's the mouse pointer? OK, so. Oh, no. First character was wrong. That's a great. Right, hello container. So this is a Java source file. It's a class with a public static void main that just prints hello world. OK, and as expected, we can compile this. Java home bin jar vac. Awesome, and then we can run it. Hello, all right, can all see that? So what's happened when I've run that is like the JVM startup has happened, and then my application's run. And I would like to time how long that takes, so we've got like a benchmark that we can use to show how it can get faster. Because this is like, the printing of hello world is nothing. The time cost there is almost all startup, right? Agreed? Good. So I use a tool called perf record -e CPU. So we're recording CPU clock events, I think. We run it 50 times. And is that all? Sudo perf. Sorry, I'm an idiot. It's not perf record. Stat. Okay, 50 times. It's going to run this 50 times so we know that we're not hitting some kind of outlier in terms of the timing. And we've got around 156 milliseconds. And it's like 1.2 CPUs, so it's like slightly parallelized, but not very much. It's 1.25 CPUs. So let's just make a note of that. Lane invocation, 156 milliseconds. Agreed? plain invocation. Plain invocation. Okay, sweet. So class data sharing, as explained, you have to generate the cache before, and you do it with Java home bin Java, and then x share is the argument that controls CDS, and you want to create the cache, which is x share colon dump. That doesn't take very long, right? And what that's done is it's created this file here, classes.jsa, which turns up in your lib server directory inside your JDK, and it is 18 megabytes in size, right? So that there's a tension there between small images and fast startup, right? Because these caches take up some disk space. 18 megabytes, well, it might not be a lot, you never know. Okay, anyway, to use it, I'm going to run the same command as I did before, but just after the Java x share dump. No, not dump, on, in this case, to use it, right? Off it goes. So up here with CDS, 1, 2, 3, with, CDS, 123 milliseconds. So just by creating that small cache file and using it, we've saved around 30 milliseconds, around a fifth of the startup time. Okay, and it was dead easy to do, and it's worked for like a decade and a half. So there's really like no reason not to do that. How to do it in a Docker file? Java CDS, yeah. You just need this line here and this thing here, right? So the rest of it is like a standard Docker file. And what's cool is this file that's generated here obviously goes into a layer in terms of like the image layers, and it's a read-only file in a read-only layer, so that file will be this, if you're running multiple containers with different JVMs, but using this same, or the same JVM, but in different containers, then this cache file is shared in the page cache between the different containers that are running. So the chances are, like from the second onwards JVM you start, that file will already be in memory, and you'll save even more than the 30 milliseconds we saw there. You'll save like the disk loading time as well. So I'm going to build that quickly, if I can remember how to use Docker. Docker build, that's F, container days, hello, CDS. Actually, I'll spell it out, because that'll be easier later. Not container, sorry. T, F, Docker file, Java, CDS. What does that mean? I don't know. Oh, right, so I don't know what perf data is. Thank you. +1. Okay, nice. Okay, so you can see here, this is the layer that will be shared, right? The layer that's created by that command is the layer that can be shared between different images as long as you all build them off the same base, right? Awesome, so that's class data sharing. So startup tip number 2, application CDS. Right? This is added in Java 10, so it's not old enough to drink. It's not even like out of nappies yet, because that was only released 2 months ago. Although before that, it was a proprietary feature of Oracle JDK. It's been open sourced and added to OpenJDK from 10 onwards. And this just does exactly the same thing, but to your application classes, right? You know, you've seen, like in terms of my application, there is a single class, so it's not going to make any difference. I'm not going to bother showing it to you. But if you've got a huge application, people running things like JEE containers, like WebLogic and whatever in containers, you can save hundreds of megabytes of memory, whole seconds of startup time. So WebLogic in a container is one of the tests, one of the startup tests that the Java Platform Group uses. And they've found application CDS to be really, really powerful there. So tip number 3, this is all the same stuff, right? Do it in advance and cache it. So AOT, ahead of time compilation. This is a Java 9 thing. So most of you on 8, I'm sorry, but when you move to 11, when that's released in September, then you'll be able to use it then, right? compile your bytecode. So when I talked earlier about the bytecode being loaded, parsed, verified, and then it's run in like bytecode interpreted mode in the JVM for a certain amount of time until the JVM's got enough profiling data to realize that this might be a hotspot, and then the hotspot compiler can compile your bytecode to native code, and then that's like the first step of the Java's sort of profile-guided optimizations that it does at runtime. But if you are someone who knows better than hotspot about what's going to happen, which you might be, then you can do this in advance, right? And again, it's going to create a cache on disk, which is going to have some size, but it's going to enable Java to start faster for you. So we'll go back, SHA, and where's my mouse pointer gone? There. The command you want to use for that is JAOTC, Java Ahead of Time Compiler. And this is my command for using it, right? JAOTC, we're going to output a cache to here, and we have to input this, which is a text file. I'll show you in a minute, telling it what to compile in advance. And you have to be quite specific. You have to give it more than classes. You have to say methods as well. And if it's an overloaded method, you have to say which overload. We're going to say which module it's going to find those in, because it's Java 9, and then -- info. Otherwise, the output is silent, and it's rather boring. So just have a quick look at the input file. It looks like this, basically, like name of class up to here is the name of the class, and then the name of the method. It's like you would never write this by hand. There are tools for creating these based on running your application and recording what happens. So let's run JAOTC. And the good news is that this only takes half an hour, so that's the rest of the talk. No. I'm running this in a VM, a Linux VM on my Mac, so it's kind of slow because I've only given it like half the host capabilities. Even so, like, who doesn't enjoy awkward silence? Takes about a minute. Hey. Good, so you don't need to hear any jokes or anything, any more jokes. In fact, that didn't take anything like a minute. It says it took 33 seconds here. It's interesting. So that's touched methods. So that's created this, and this is a shared object file in standard like ELF executable format. The classes.jsa we generated before, that was just serialized memory, but this is a shared object file. So you can inspect it with your debuggers and things if you like. And to run it, I'm running perf again, perf stat minus ECP clock 50 times. You can use CDS at the same time, so xshare on is still going to work. And then you do, sorry, it's split across the line, -xx AOT library equals that touch methods.so, and then your regular arguments. Right? You just run it. So with CDS and AOT, 101 milliseconds. So like that's the third of the time off, and that's without AOT, without app CDS, which can make a much bigger difference if you've got a large app, and most apps are larger than my Hello World, right? So those things are not like, I don't think they're super difficult to do. If startup time is a concern to you, like go ahead and read. If you look me up on Twitter here, on my profile, there's a link to my blog where I go into a lot more detail in a couple of posts about how to do that for yourself with your own code. I use some closure examples for app CDS where it has like halving the startup time kind of effect. So it's worth looking at. Okay, how are we doing? Sweet. So the next thing after fast startup is small images. And they're not totally unconnected, right? Because smaller images start faster. Firstly, like copying them across the network has to happen, presumably, at some point. And then there are startup costs. The size of the image affects the actual startup, even if the image is already on disk. also, like maybe you've got some quota in your Docker registry that you need to worry about. Like no one's ever going to say, I don't think anyone's ever going to say that larger images are better for any particular purpose. So small images. So what's in an image? Well, I guess maybe you can remember from my Docker file a minute ago what I put in it. There's these things. There's an operating system like you from some base Linux distribution thing. Add the JVM, add your code, add the JDK, I should say, like all the core classes in the JDK, add your code, and then typically like a little bit small at the end, but still optimizable, is the JVM itself, like the actual binary executable of the JVM. These are all optimizable. So let's see. So what, I don't know, can we have like, what's a popular base image to use a bit underneath a Java Docker image? Like from Ubuntu? It's from scratch? So, and what do you put in from scratch? Uh-huh. So you know about Project Portola? Ah, interesting. I wonder how you, okay, I'll talk to you afterwards. You're smart. Okay. So Portola is a build of the JVM for Alpine Linux, right? So because Alpine uses musl instead of glibc, the regular Linux x86 64 distributions of JVM don't work, and you will need a special build. And Project Portola is such a special build. Perhaps there are others. Perhaps you build the JVM yourself. So compared to, like you saw in my Docker file earlier, I said from Oracle Linux 7 Slim. Even the Slim version is 120 megabytes. Alpine's 4. It's like there's no competition, right? Because you, as a Java programmer, you don't care like what's in the OS as long as it can run the JVM. Everything that you do is like that layer above, unless you're doing something like non-standard, I guess. Well, in which case, like you've got a specialist use case. But most Java applications just live on top of the JVM and use the benefit of the abstraction it gives you away from the OS. You don't care as long as it can run the JVM, and that's what Portola and Alpine and musl are working towards. Core Java. So there's a tool called JLink, and if you haven't looked at Java 9 or 10, maybe you don't know about JLink. Anyone know? Anyone looked at JLink? Right, I'll tell you about JLink then. Right, so the big thing, like I said, in Java 9 was the modularization. So they took the whole, all the Java core classes, bundled them up into modules, and enumerated the dependencies and the types of dependencies between them, and thus Project Jigsaw, the way they all fitted together, is the modular JVM. And like brace yourselves if you've seen dependency graphs before. Right. It looks like this. Actually, this is like 1/3 of it. It looks like this. So there's more, right? There's a lot more. I'll show you. If you look in, so Java Home, JMods, all these JMods, right? Java modules. How many? 76. And I guarantee, like, even if you tried really hard, you wouldn't write an application that used all the modules that are available. In fact, you probably use hardly any of them. If you're writing server-side Java, you don't use the UI widget tree thing. If you're writing Java since like mid-2000s, you might not be using the XML parsers. Like, who knows? There's a lot there. There's a lot of crypto that you might not be using. There's a lot of hardware support, and I think there's a lot there that is like very rarely used. And JLink is the tool for stripping it out. Okay, and the effect can be like this. So here's the full JDK. It's 568 meg. I forget exactly which version, but they're all about the same. Java.base, which you can't like not use, 46 meg. And then Netty, this is a profile that contains enough modules to run Netty, the web server. 60 meg, right? So there's 90%. If you're just running a web server, there's 90% of the JDK that you're not using. You don't need to add into your builds. JLink is the tool for getting rid of that, right? I'll show you it, because I've got time. So let's go up. Docker, oh God. Docker file, Portola. Can you read that at the back? We're all good? Nice. OK, I can't read it. OK, so we're using a multi-module build. No, multi-stage build. OK, so to start with, from Alpine, where's my mouse pointer gone? There it is. There it is. There it is. So from Alpine latest as build stage, right? Add this, which is the muscle build of the JVM that I was talking about. Add it to the path, and then we run JLink. Okay, JLink can optionally compress, as in like gzip compression, the resulting files that it creates. So it saves even more space. These are where the modules are. These are the modules we need. And I know for my hello world, I'm only going to need java.base. If you've got a bigger application, you can use a tool called jdeps, which will tell you which modules you need by static analysis. And the output goes in this directory here. And what's going to go in there is like a whole new Java distribution with all but one of the modules removed. Next, start again. And then from the build stage, just copy in that. We don't need the whole JVM, right? We're copying in that. And then the same as before. OK, so if I run that, Docker build, container days, hello, Portola. Is it not called that? Dockerfile, what did I call it? Oh, Dockerfile Portola, probably. Yeah, there you go. Sorry, I did practice. OK, and because I built it before, like it's all come from the cache. But if we look at what's been generated, right, the Hello CDS one that I created earlier was 0.5 gigabyte, and this one's like much, 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 much smaller. And it does exactly the same at runtime. Okay, so why not?
Does this affect runtime?
No, well, as long as you don't use any tricks like reflection to get to modules that couldn't have been statically analyzed, no. It's just the files that you don't load aren't there. As long as you know you're not going to need them. And if you're using modules with your own code, then you won't be able to, because modules have stricter encapsulation about not being able to reflect onto things in other modules. Oh yes, your code, right? The next smallest thing is your code, and that's your problem, basically. Just write less code. But also, don't use such large dependencies. You don't need to bring in a commons library that's 15 meg if you're only going to use one single method. Just write it yourself, or did I say copy and paste it in? No, but just think about it, right? The dependencies are not just free stuff. And then the next thing, the JVM, and you're thinking, how can we use less JVM, right? Surely we need the JVM. So there are two things you can do. Firstly, there are arguments to JLink. When you run the JVM, it's got a garbage collector built in. In fact, it has several, and you only use one, right? So there are arguments to JLink. You'll have to read the docs. But there are arguments to JLink to literally remove garbage collectors that you're not using, right? And these take tens of megabytes of size. If you're at that level, why not? But the most extreme is this new project, Substrate VM. Substrate VM is a entirely new virtual machine. It's written by Oracle Labs, and it's part of the Graal VM project. So who's heard all the kind of news about Graal recently? A little bit. So Graal is the main part of it is a new compiler to replace the hotspot compiler, but it also has this new VM in it as well. And that takes your Java code, subject to a closed world assumption, so no creation of classes at runtime, no loading classes over the web at runtime, which you obviously wouldn't do because it's crazy. Subject to a closed world assumption, it can compile your Java code and itself into a single statically linked binary, and those will be for most smallish applications, single-digit megabytes in size. And you can just put those in a from-scratch container like you would do with a Golang binary. So check it out. If you can live with that closed world assumption, I know for a fact that the Oracle Labs team would be keen to hear of people using Substrate for this. OK. Next, respecting the environment. So like I said, Container is a sandbox. There are rules. You're not allowed to do all the things that you would be if you were a process just running on the host. And if you don't respect those rules, you're going to have a bad time. In particular, the JVM does a lot of self-tuning, right? The JVM is 20-plus years old application. It tries to cut down on the amount of configuration you have to do by using this process called ergonomics, which inspects the available hardware and tries to right-size some things, in particular memory and CPUs. It looks at that and tries to set stuff up so that it's using the hardware effectively. And the way that hardware is detected is different if you're inside a C group limited container than it is if you're just on the host, right? So this is not like free. The JVM has to support it. So based on the detected memory, the heap size can be set. If you don't set it yourself, a heap size will be chosen for you, and it will be based on what the JVM thinks of as the available memory. Garbage collection region sizes, depending on which GC you're using, it splits the heap up into regions and moves objects between them, depending on how old they are, and those sizes are controlled, and the number of regions is controlled, depending on which GC you're using. And then compiler cache areas, I've called them. So when your code, the bytecode is compiled into native code, there's a certain amount of memory reserved for that compiler to work. And that size of those is selected by ergonomics as well. And you can override all this with flags, but the idea of ergonomics is you don't need a shitload of flags, right? You just run java -jar and it does it for you. Generally, it's successful. Based on the detected CPUs, garbage collection compiler thread count is set. And then there's this method here, java.lang.runtime available CPUs. So that is supposed to be a call. It returns an int, and it's supposed to be a representation of how many threads can be working in parallel on the hardware. And so a very, very common, you might say like the designed use case for it is for sizing a thread pool, okay? Because a thread pool that's too big will have too many threads running, and there'll be context switching in and out and swapping on and off the hot path, and it'll actually be slower than having the correct number of threads. So if that's wrong, the implications are pretty bad. So containers have this restricted view, and it's not free, right? The JVM has to look in a different place. If you just look into like proc mem info, you'll see the host's memory, even if you're C group limited to only be able to use a bit of it. So since JDK 8, this is good news for you, right? Because you don't really need to do anything except use a new version of Java. So since JDK 8, that's been improving. JDK 8 and 9 had some awareness of C group memory limitations and this kind of thing. And it was behind --XX, unlock experimental options, blah, 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 a couple of those. Since Java 10, i.e. March this year, those are like on by default, and they will be on by default in 11, obviously. And there's more, right? There's more and more and more stuff. Being able to use the tools that you use outside of the JVM to connect in and to inspect running JVMs, they didn't work initially for containerized JVMs because the process namespace was different. Metrics about how much of the C group limited memory is being used versus how much of the host memory is being used. All these, so there's lots and lots of these kinds of things. And this last one is particularly interesting. Oh, sorry, shit. This last one's particularly interesting, right? Because the way of limiting CPU, there are many ways of limiting CPU. You can pin a container to a particular CPU, or you can give it a time slice thing. And Kubernetes has a particular way of doing it, which this last one is optimizing for detecting that we're running in that kind of environment, such as the one that Kubernetes sets up, and setting the thread pool sizes and runtime.available CPUs correctly. So, Java in containers, yes. Duke's got his coffee and he's like happy about it. The Java platform group are like absolutely committed to following the industry and in terms of like how they use Java. And containers and Kubernetes are becoming like de facto standard ways of deploying server-side applications. And so the Java group is totally committed to like making it work well in that environment. So thank you for listening. I think that's about time. It's me. Check out FN Project, remember, which I work on, and check out Project Portola, which is it's a new thing actually in Java with Java 11 that will be released, hopefully, if it's popular, which it should be. So anyway,
Thank you.